All right, everybody. Good afternoon. We are live. Sorry, we had a little bit of a couple little technical problems getting the. All right, everybody. Good afternoon. We are live. Sorry, we had a little bit of a couple little technical problems getting the. So, we are now. So again, sorry for the echo. We are now we're now live without the echo. So welcome everybody to the Gupta College of Science here at Coastal Carolina University. Today, of course, we're very excited here in the Physics and Engineering department because this is the day that we land our new rover on Mars, Perseverance. It's been a process. It's been a 9-month journey of almost 293 million miles. And we're really only about 30 minutes away from 38 minutes and 37 seconds away from landing. So, where this is it's been a long time, been a long process to get this going, and we're very excited to get the newest technology on Mars. My name is Ian Hewitt, and I teach astronomy here at the Gupta College of Science at Coastal Carolina University in Myrtle Beach, South Carolina. And I thought I would just take a few minutes to kind of explain what we're going to see, and then what a little bit about the rover. And if anybody has any questions and they post them on, you can post in the comments and I'll try to answer them. And then when we get a little closer to the landing, I'll actually cut over to the JPL mission feed and kind of give you a little bit of narration about what's going on. I have my headphones on because the sound is better, but I also have my earbuds in underneath the headphones, and I'm listening to the controllers talk amongst themselves about for the landing, so that I can kind of interpret what's going on for everybody. So right now the spacecraft, so the rover with its cruise stage is approaching Mars. It's looking very good so far. They had a briefing a few minutes ago that said it's right on target. So what will happen next? Well, let's actually talk a little bit about the rover. Actually, let's first let's talk a little bit about the rover, and we'll show you what happens next. So hope you can see my screen. So this is an artist impression of the Perseverance rover, and this is a nice picture of Mars. This is interesting. This actually was taken by an amateur astronomer called Damien Peach from the UK. And so it shows you how much technology is really advanced, that you can get some really great pictures even with an amateur telescope. Of course, we have rovers on Mars, right? So we have Curiosity. It's been on Mars since 2012, so really 9 years. And Curiosity spent a lot of time with the geology, trying to identify habitable environments, right? Water, key chemical ingredients for life, and sources of energy for life. So this is, Curiosity did a great job of actually identifying the fact that Mars used to be very wet. In fact, Mars used to have oceans. So that's that really positive. So the next step is to go forward with a new rover, which may look a lot like Curiosity. I mean, when you look at it from the outside, they look like twins, but the technology is much different on this rover. It's more advanced technology, and the science instruments are organized a little bit differently. Of course, we still do geology. That's an important component. And of course, but this rover will also look for habitability and biosignatures. It's actually going to look for the markers for life on Mars. The other thing it's going to do, which is kind of interesting, is it's actually going to take samples, and I'll talk about it in just a second, and encapsulate them in little tubes, and actually basically stash them, build little piles of them on Mars, so that a future mission can come and return them to Earth. So we'll be able to get samples from all kinds of locations, pull them all together, so some spacecraft can land, load them in, and fly them back to Earth, which would actually be really, really cool, because once we get these samples back to Earth, we can investigate using all our technology. The other thing is very important, is to prepare for human exploration. NASA hasn't forgotten the fact that eventually we will have human missions to Mars. There are a lot of things we need to know that we don't know. And then there's some technologies we need to test. And this rover will do some of that. I always like to put this slide in. So these are a couple of the folks at JPL that posed for a picture for us. And to give you an idea of the rover size, originally the Mars Pathfinder rover was basically the size of a large remote control car. That's the one down here in the corner. And now I'll go ahead and circle on my pen. And then when we sent the Spirit and Opportunity, which went up in 2003, were much, much larger, like this size. When you start talking about Curiosity and now Perseverance, they're on the right here. They're the size of an SUV, and they're about 2,500 pounds. So they weigh about as much as a light SUV. So there's a lot more technology and a lot more capability you can pack onto these rovers. For example, the primary mission for the Mars exploration rovers was 90 days. The primary mission for Curiosity and for Perseverance is actually a year, and they're expected to last probably closer to 15 years. So there's build a lot more in when you have more space and more robustness. So again, it looks like Curiosity, but it's a lot different in terms of the improvements and the technology. I mean, it's almost 10 years difference. And if you think about that, you think about what it would take for like cell phones or computers. Think about what a cell phone or computer looked like 10 years ago. There's been a lot of technology updates. Technology doesn't proceed quite as fast for spacecraft because it still has to be radiation hardened and everything, but the instruments are much better and much more focused on the newer tasks. So just kind of a quick overview. I won't actually go through all these instruments, but you can see it has basically all over the outside, it's got various instruments that will analyze Mars. And you can see the main feature is the robotic arm out front, which has a very large instrument pack, much larger than Curiosity, so that you can actually take this instrument pack and you can put it up next to rocks or something you want to analyze and get some really close-up readings. So you can see there's lots of abbreviations. They do like Sherlock. NASA loves to name things. Moxie, they love to name things with neat little acronyms. So what to expect today? What are we going to see today? Well, basically what you're going to see is what's called entry, descent, and landing is the technical term for it, or EDL. Another way to think about it is I call it the three zeros problem. Basically, you're going to want to take 3 zeros of speed off of the rover in order to land it. So as the rover was flying closer and closer to Mars, it gets caught in Mars' gravity well, and Mars starts pulling on it. The gravity starts getting stronger and stronger. So it starts speeding up and speeding up and speeding up. So what happens is by the time you're basically almost hitting the atmosphere, you're going somewhere between 12 and 13,000 miles an hour. That's fast. So what you need to do is now you need to slow down, because you certainly can't land on Mars going that fast. Otherwise, it would just be basically game over. So what the first step that you're going to have is you actually will enter the top of the atmosphere, and they'll use a heat shield and atmospheric friction to slow the spacecraft down. In fact, that's so effective that it'll go from like 13,000 miles an hour to around 1,300 miles an hour. So 10 times slower. Once you're at 1,300 miles an hour, and that's sort of like about Mach 2 or a little less than Mach 2, so you're still supersonic at that point, it will deploy a special parachute. And this parachute will enable, this parachute was designed specifically to work in the Martian atmosphere and to work at these really supersonic speeds. There was a lot of testing done in some very large wind tunnels out at Ames in California. And basically this parachute will slow it down to about between 200 and 300 miles an hour. So again, here's another zero we've dropped, so 10 times less speed. So once you do that, basically this whole back shell assembly will actually separate off. And once it separates off, basically it's going to drop out this little pack, and this pack is going to have like this rocket pack with the rover tucked up inside of it. So then this pack will actually, the rockets will fire and will start slowing things down. And again, this will be the last element to really slowing it down. So going from like about 200 something miles an hour down to a leisurely like 5 or 6 miles an hour. So as that rocket's firing, what will happen is it will drop the rover down on a bunch of cables. And this is what they call sky crane mode, because it kind of looks like a crane. And then by the time it touches down, it'll touch down the rover at like 3 miles an hour. It'll only be going like 3 miles an hour. The second the rover touches down, it will sense that. The second the rover touches down, it will sense that it's hitting the surface, and then what it will do is it will actually the cables will be automatically cut. And once those cables are automatically cut, that sky crane will fly and try to get as far away from the rover as possible, and then crash some distance away. You want to do that because you certainly don't want to damage the rover, and you also don't want to contaminate the scene with all kinds of rocket fuel. So basically, that sky crane will fly as far as it can to get away, and then basically you're on the surface of Mars and ready to go. So the good news about this, as opposed to some of the previous rovers took like a couple of days to like unfold and set up before you could get any pictures or anything. Usually you can get pictures back pretty quickly because the rover is basically set down on the surface. That's it's one thing to hear about that, but I've also got a very short video. This whole process takes about 7 minutes. But I've got like about a 3-minute video that kind of shows you basically what was going to happen. So let me show that to you. Okay, this is of course an animation. So the first thing you should see, of course, you see the spacecraft, and you should see this cruise stage, which is part where the solar panels separate. In real time, that's about to happen very shortly. And you can see that there are rockets in the back because you want it faced directly into the atmosphere. You don't want to turn over, because if you do, you'll start tumbling and you won't slow down. Of course, if you were on Mars, you'd get a really great view. Imagine how this would look, seeing this thing streak through the sky, slowing from 13,000 miles to 1,300 miles an hour. You see it's still trying to kind of keep itself oriented. Now here's the parachute. Again, the parachute takes it down to around 220 or 250 miles an hour. Still pretty fast, but nothing compared to the 13,000 miles an hour when it's entering the atmosphere. So then the drops off. Now you get the rocket side. Once it's confirmed it's on the ground, the sky crane flies away, and the rover is essentially ready to go at that point. And then really all you need to do is raise the mast, and you are in business. So again, in reality, that whole process takes about 7 minutes. This video is a little bit shorter, so that just to give you an idea of what's going to happen. So I'm going to go ahead and stop that and go back to the. So one of the things that's different about this, the original Mars rovers, when we first started landing them, like way back in Pathfinder, it was just like anywhere on the planet's fine as long as it lands safe. And then, as we started doing the Mars exploration rovers, we had like these 1,000 or 2,000 mile ellipses and tried to narrow it down. So this rover has new technology, so it's able to actually be a lot smarter about how it lands. So once that back shell drops off, what it will do is it will start taking pictures, and it will use basically the equivalent of what's called plate solving software, which means it will compare the landmarks and the features it sees to things that are in its memory, and it will try to determine where it is and basically try to basically narrow down the landing ellipse a lot. So basically it's going to be smart enough to say, hey, I've got to fly farther this way, or I've already flown far enough this way, so maybe I'll just stop and just kind of start going straight down. So it's also smart enough to avoid any kind of pitfalls. Like, you would want to have like a really sharp mountain or big, huge, sharp rock that you don't want to drop the rover on top of that, right? So um, this is actually a newer technology. It's much better in the Perseverance rover than it was before. You might ask where it's going to land. Well, it's a place called Jezero Crater. And so this is basically a map of Mars. As if you took the surface of Mars, you kind of opened up Mars and laid it out flat. This is what you see. And this kind of shows you the various places where previous probes have landed. You see the Viking probes from the 70s. And then you see Opportunity and Pathfinder, so Opportunity and Spirit, rather, the original Pathfinder. And there's Gale Crater, and this is where Curiosity is near here. And so this is the area here. So what makes this area special? Why do we want to do that? Well, one of the things is this area is a very likely place where there was a lot of water early on Mars. And when you look at the picture, and this is colored to show you like certain chemicals, chemical signatures, but the terrain, you can look at the terrain and it looks an awful lot like this was shaped by water. You can see like there's like almost looks like there was a river here branching out into some sort of delta. And this really very much looks like alluvial features that you find here on Earth. So the thing about it, because it was wet at one time, it's likely there might still be water underneath, and that's a very likely spot to find potential life. So it's a very interesting site that we want to explore. There is a secondary site called Midway, and again, some that comes up with that we can drive to. It's also got some really interesting features. So they're looking at a long-term mission. Of course, a big part of sending the rover there is cameras, right? We need to see what's going on. The rover actually has 23 cameras associated with it, and 9 of them are engineering cameras, which are basically going to be dedicated to making sure the rover doesn't have any problems or run over anything. You see them, most of them are labeled HAZ cams here. And these are basically cameras on the bottom pointed down that are looking at the ground, and the computer on board is using those to make sure that nothing dangerous is happening. Like if it's about to drive off a cliff or drive in a big hole, the actual rover will stop itself no matter what it's commanded to do. You may command it, you have to go forward, 300 feet. It may start going, it may get 20 feet, and it may detect like a crater or a big rock. And the rover actually is designed to be paranoid, and it will stop. And it will send a message back saying, I stopped because I saw something really dangerous. And of course, you can use those HAZ cams to show what the rover is seeing. So, of course, you can't do that in real time. It's not like a video game with a joystick controller, because of the light travel time to Mars. Currently, the light travel time is around 7.5 minutes, which means we talked about that 7-minute EDL sequence. Well, the problem is that by the time we see it starting here on Earth, it's already actually really finished. And with a 7.5 minute round trip time, 7.5 minute light time, round trip time is 15 minutes. So that means if you were actually trying to drive it with a joystick, like a video game, Imagine trying to play a video game, but there's a 15-minute delay. You see something coming, you have to 15 minutes in advance, you have to turn, and well, the odds are you're probably going to crash. And if you crash on Mars, you can't flip it over, and there's no reset, there's no extra lives, there's no power-ups. Basically, it's game over. So it's designed to be very careful. The other big cool feature is that, of course, there's cameras actually on the arm, so you can get up close and personal with any kind of rocks. And the other thing, that one of the cooler things is above this mast, the mast cams that they have, the mast. So they have a mast sticking up, and it has like the head of the rover, if you will, and it has some navigation cameras. It has a telescopic camera and a bunch of other cameras, so that you can actually take really nice 3D high def images. So this is just a picture of the HAZ cams. You can see them right here. And you know, they do point at the ground, and they are meant to look at things. One of the coolest parts is the super cam on the mast. And this is the same thing Curiosity had something, although this one is actually a little bit better on Perseverance. It uses the fancy technique called elemental analysis through laser-induced breakdown spectroscopy, LIBS. And basically, this is the short version of this is a technique that lets you analyze compounds from a distance. It uses sound and light to identify compounds remotely. So the thing about it is, you can really characterize something while you're still 7 meters. So that's like a little over 20 feet away. You can really get information. That's pretty cool. It can look down to 0.5 millimeter. So really like a little tiny pinpoint. If you think about like a pencil lead and a refillable pencil, a lot of those are like 0.5 millimeter. So that's a very fine resolution. And so the way this works, laser-induced spectroscopy, is that there's actually a laser on the mast cam. So yes, we actually do have a laser on Mars that we can fire at things. How cool is that? Wouldn't that be fun to be the person to operate that? And so what happens is, it will basically, the laser will actually shoot at something, a sample, and it will actually vaporize part of that. So basically what will happen is, and I'm sorry if I pause, it's because I am listening to the JPL controllers on another loop and listening to what they're saying, and they said that it has switched the spacecraft has switched to tones, which is like it's basically it's thrown away the back part of the spacecraft now. So it is in the process. We're working on getting there. So that's totally expected. So the basically the laser will actually vaporize part of the rock, and then the light coming through the rock, you look at it through a spectrograph, and you can see what that the vapor of the rock is actually made out of. So yeah, it actually does shoot lasers at things on Mars. The other thing is that caching system I talked about, which basically has a bunch of tubes that you can take core samples with out of rocks and things, and then basically seal them up. And will actually give a hermetic, completely waterproof, airproof seal. And basically there are a number of, 43 sample tubes. And what it will do with these sampling is actually build up a couple of caches. It'll build a couple of piles of these, right? So what it will do is in the future, we'll be able to send an a spacecraft to Mars to land near the cache, and basically pick up the tubes and put them in a small capsule and launch that capsule back to an orbiter, and then actually bring that orbiter back to Earth. So we'll actually be able to analyze those. So I'm hearing we're about 5 minutes from entry interface. So we're about 5 minutes away. So let me just jump right ahead to a couple things, talk about three really cool things. First of all is META, your Mars weather station. So Perseverance has a really cool weather station on board that it will take like regular measurements of temperature, humidity, radiation, and dust size. Why is dust size important? Well, dust size is important because if you're going to operate equipment on Mars, like you send human exploration, it matters whether it's small or large. what type of dust it is. Also, some particle sizes are very bad for humans, and some particle sizes you can tolerate pretty well. So we need to understand that, and it will constantly measure those, so not just periodically. And humidity and wind, and all these kind of environmental temperatures, especially the radiation, will tell you what you will need if you send humans to Mars, because you'll know about the environment on really like every few minute basis, not just on a daily basis. The other thing that's really very cool is the Ingenuity helicopter drone, and this is a test technology. So this has a huge potential. It's very difficult to make things to fly on Mars because it has to be light because the atmosphere is very thin. In addition, the rotor blades have to spin very, very fast. So this is a test drone that Ingenuity will carry, and it will deploy it. And this drone will fly along with Perseverance and check it out and be able to look at things and be able to make sure it works well. This is really important both for uncrewed missions and human missions to Mars. For uncrewed missions, imagine if you had a helicopter drone with all kinds of instruments. So instead of talking about going 3 or 4 miles on Mars, you could go hundreds of miles on Mars. Also very important for human exploration, because there's a lot of places that humans can't really go on Mars, down in holes or down in valleys. And thing is, if you had a drone you could actually use, that would actually be really huge. So again, thin air needs to be light, needs to spin very, very fast. The other thing that's specifically for human exploration is called MOXIE. And basically what this is, if you ever seen the movie The Martian, this is the same kind of technology. In the movie The Martian, they had oxygen generators that took the Martian atmosphere and created breathable oxygen from it. That's exactly what this does. This is a test platform that will actually generate oxygen using a electrolysis process. And this is specifically for human exploration, to say, yes, we can do that. Because if you don't have to carry your own oxygen, you can actually generate the oxygen. That means if there's a problem, you can generate more oxygen than if you need it, and you don't have to carry all that weight. It's a really important part. So, okay, so I'm thinking the one thing I'll say, the last thing I think I'll talk about here is the communications. This has curiosity, but in reality, this Perseverance works the same way. In the early days, we had to rely on the spacecraft just talking straight back to Earth. And that's kind of challenging with the dish trying to get pointed exactly at Earth, especially after landing. But now we have a series of spacecraft in orbit around Mars. And these spacecraft are acting as relays. In fact, when Perseverance lands, it will actually be on the side of Mars. It's not facing toward Earth, but these spacecraft will actually be relaying information to us. So we actually have a communication satellite network that we can actually use. And you can use these UHF relays. And for those of you that may be familiar with it, if you see the little handheld portable radios that like police or firefights carry, that have the small little rubber antennas that are about that tall, that's all you need for UHF communications. And they're omnidirectional. You don't have to point them. So right from the get-go, it'll be talking to those satellites. So what I'm going to do here is let's talk a little bit more about this. I'm listening, and so they are still waiting to reacquire the signal because so far everything's okay. So just real quick, we'll talk about the Deep Space Network. These are the large dishes that will receive data and will send commands to the rovers. There's 3 large ones that have these very large dishes. And I know it's really hard to tell how big this dish is, but if you look at that, that's that you can drive a pretty large truck into that building right there. So that tells you how big the dish is. The 3 centers are in California, Spain, and Australia, so that any given time we can be talking, anytime it's toward us, we can be talking to it. Okay, so while we're still waiting for entry interface, I will cut over to the JPL feed when we get things that are happening here. Let's talk a little bit about how they actually drive this rover, right? So again, we talked about the fact that you don't drive it like a remote controlled vehicle, right? It's nothing like that. The way it does is basically there's basically the rover wakes up, you know, from overnight. It usually doesn't do a lot during the nighttime hours. And then what it will do is it will actually download a whole bunch of information or send up a bunch of information to both the satellites and Earth. And basically, it's going to be all kinds of information that says, here's where I am, here's everything that happened yesterday, you know, what next, right? So then it actually starts this process that goes on every day during the primary mission. So all that information comes in, it goes to the engineering team, who basically does a quick assessment of what the status of the rover is. And then what it does is that will go to the science team. And so that they'll ask the science team, what do you want the rover to do today? And they've got maybe about 2 or 3 hours to decide what they want the rover to do that day, and say, okay, maybe we want to drive over here and do something. And then, but that goes back to the engineering team that figures out what is possible to do in the next day. Because maybe they'll say, well, everything you've told us to do, that may take 3 days. So they'll say, this is what we think is realistic to do the next day. And one thing to realize is that a lot of people think the rovers move very fast, right? Like they can picture these things like kind of bouncing across Mars, leaving a big dust trail. If you were on Mars watching these rovers move because they are so paranoid, it would be very, very, very dull, because they move very slowly and very deliberately. So once the engineers figure out what's possible to do, then it goes over to the Mars rover drivers. And they basically will encode the commands up for the spacecraft, and then basically they will send that up. And so then they'll uplink the commands for the next day, and then that's what happens. And then it will try to run, and there you go. So basically, basically this goes on every day. The weird thing about doing this, if you ever work on the Mars team, I know lots of people who do work on the Mars team, is that the Mars day is longer than the Earth day, just a little bit, right? Like by about 26 minutes. So what that means is every day your timeline shifts by like 26 minutes. So like one day you're coming in and this process starts 8 o'clock in the morning, next 8:26. So pretty soon it'll move to the point where you're working overnight. So you get this really weird time schedule that sort of shifts as time goes by. In fact, they actually had a jeweler in Tucson make some watches that actually keep Mars time so that people would know when to go to work and when things were happening. Okay, so I think I'm going to switch over, see if we can switch over to the feed. So let me okay. Okay, so this is actually what we're doing. So actually, we'll pick this up now that we're. So right now it's entering the atmosphere of Mars. So
Amarillo has lost log.
Properly indicate reversal, bank reversal.
We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its
max
distance
10
to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
Amarillo has lock again.
Right, so you're getting about
indicate reversal.
10 Gs of Earth acceleration, which is a little bit. The thing is, this would work great for robotic spacecraft, not so great for humans. They'd have to slow down a lot less, and take a lot more time to slow down.
Perform bank reversals in the atmosphere to control its distance to the landing target.
Probably reversal.
One thing you may notice if you look around the room, there are various. You'll see peanuts, and you kind of see some. You'll see some wipes there, but you'll also see some peanuts lying around. That's actually a tradition inside
Perseverance is
JPL.
going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
And if you look at these boxes, these meters at the bottom, you'll see that the speed is really slowing down. So you're only going about 4 times the speed of sound now, 4.63 Mach. So we're slowing down rapidly. And this, of course, is animation. These aren't live pictures. So again, remember, we are like 7.5 minutes light time delayed. So all this happened 7.5 minutes ago. So whatever is going to happen has already happened. So it's one of the things that makes this very nerve-wracking.
Is about 550 meters per second at an altitude of about 15 kilometers from the surface.
And notice we've already gone down to 2.36 Mach. So we basically halved our speed.
MRO's reporting good telemetry log.
When they talk about MRO, that's one of the satellites.
We are starting the straighten up and fly right maneuver,
UBMD jettison,
where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
Okay, so the parachute has come out.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is.
So that's excellent. That's good. That's good news. That means the parachute has worked.
About 12 kilometers from the surface of Mars.
So you can see now we're below
heat shield set
1 Mach. Okay, the heat shield has been thrown away now. This is actually a really good sign.
The heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So we're going roughly about 400 miles an hour right now. If my math is correct. And it will not be long now before we find out if
net filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
So really, they're only about 3 miles up now. So
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming.
All right, so now the cameras have looked and it now knows where it is.
Of the landing engines.
Back shell set.
Is 83 meters per second at about 2.6 kilometers from the.
All right, so now the rocket sled has dropped off.
We are currently performing the divert maneuver Current velocity is about 75 meters per second at an altitude of about a kilometer.
When they talk about the
off
divert
surface of
maneuver, it
Mars.
actually kind of tilts over to the
Here,
side to
50
get out of the way of the back shell and the parachute
have
coming down because you don't want to get
Completed our
tangled
terrain
up.
altered navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
SDS level.
Constant velocity
104.
accordion. Constant velocity accordion, altitude air.
We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
So it means it's about ready to drop the rover on the cables. So
Throttle down.
the picture behind me.
Sky crane maneuver has started. About 20 meters.
Tango
off the surface.
Delta.
Okay, Tango Delta means they have touched down.
Nominal.
That means that we have landed. The Tango Delta signal is the one you want to hear.
From MRO. Bring stable.
UHF is good.
Okay, when they say UHF is good, that means it has
Touchdown confirmed.
it has
Perseverance,
contacted the
on the
orbiting
surface of Mars,
spacecraft.
ready to begin seeking the signs of past life.
So very exciting.
At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
So again, remember, it's on the other. It's not in the side of the Mars that's facing Earth right now. So it's having to talk through the satellites. So that's actually very good news. So yes, so basically we now have a new rover on Mars. So
More reports, they're still getting telemetry from the lander.
after a trip of about 292.6 million miles
All right, I'll
in
stay
9
tuned.
months.
Touchdown confirmed. We're going to wait for the images.
So we're going to stay on a few minutes because one thing about this having the satellite network and having the rover that kind of sets down, it's already basically set up. They'll try to get an image back pretty quickly. So wait just here a couple of minutes and we should have an image. So the first image from Perseverance, which will definitely confirm that everything's working fine. For those who may be curious about how the rover, the computer on board the rover, the computer has to be able to tolerate some pretty harsh environmental conditions, down to minus 200 degrees at night, and also some pretty serious radiation. So it's not basically
OL1, you have what you need?
like a PC. It's not like a PC motherboard.
I have what I need. We have seen the completion of EDL 3000.
It uses the.
Copy activity. That is.
I'm going to turn down the sound just a little bit here. So it basically uses a Power PC like the Macs. If you go back, what about 10 years ago, the Macs used Power PC processors. Uses one made by IBM called a RAD 750, which is a radiation hardened processor. It runs about 200 megahertz. So they do all this on would be considered a very ancient computer. Your cell phone has probably between 4 and 8 cores running at 1.2 gigahertz. Okay, we have a picture. I'm sorry, the picture. So let's see if they'll give us.
Flight, this is OL3. I have the target point on the map when you are ready.
We are ready, OL3. Go for it.
So.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
Okay, so they're basically looking to show where they've landed. So there you are. Look at that. Very nice. No big rocks, no big holes. So that is showing that everything's certainly working pretty well on the rover because you're able to get that picture back so quickly. Of course, it's not a nice color high def picture. You'll be seeing probably one of those very soon. What you're seeing, some of the other images you're seeing that look like they're taken from above are probably coming from the cameras that took pictures that it took while it was landing, or cameras took pictures.
Can we get the image, OL?
So let's see what.
Activity, this is OL. Can you repeat that request on N20 EDL off?
Oh, well, can we get the other image? Should show the cliff.
Okay, so they apparently got a second image. So let's hang in there and see what that looks
say
like.
What image again? I'm not understanding.
Flight OL3.
OL3.
You can see we've landed about 35 meters from the nearest rocks that we could identify from orbit by their shadows.
Copy OL3. TRN.
So now they're basically confirming, you know, where they landed, and looks pretty much like where they thought they were landing.
Desiro.
Flight. I remember this spot. It looks good.
So good news is they actually recognize where they are, so that they didn't actually end up a long way away. So we ended up right about where they should. Oh, there's another image.
You recognize them all. So.
So, you know, you'll notice they'll be moving the screens around a lot. Again, this is the mission control feed. This isn't a highly Hollywood-produced feed. So basically just kind of show...
Electra's still in lock with the lander.
This is basically just kind of seeing what they're seeing as soon as they see it.
Surface. EDL is done.
Okay, so that's the official call.
Transition to surface.
That they are now moving away from the EDL phase, the entry, descent, and landing phase, into surface operations. So they'll actually switch modes now and switch to surface operations. That confirms everything's landed and everything seems to be working fine. And the whole navigation people will be handing it over to the ground operations team so that they can start actually exploring Mars. So that's great news. I'd like to thank everybody that that came and joined us here today to watch the Mars lander. So I'm sorry I didn't have. It looks like the comments were not working, so I couldn't take any questions. But certainly, you know, NASA has a great website called Mars 2020 that talks all about the spacecraft, and we'll have all kinds of good images as we get them, and you should be expecting a lot of really cool things coming back from them. Okay, well, thanks everybody again for attending, and I hope everybody has a great day. This is Ian Hewitt from the Gupta College of Science here at Coastal Carolina University, and wishing everybody a good day. Thanks.
Ian, can you hear me?
Yes, sir. Can you please stop the live stream?